pleasure to have the opportunity to participate in this delightful event. So my topic is flat space holography, and it's been a natural question for 25 years to seek a holographic dual for Minkowski space-time theories, because the dual discovery of Maldacena concerning CFT duals of gravity theories in ADS has been so influential in the development of theoretical physics. So I will give you an introduction to some of the progress that's taken place in this endeavor. But first I want to say a few things about Mike. So our lives have intersected on several occasions, but most notably in the period when Michael was a Caltech graduate student, and I had the pleasure of being his advisor. He was my advisee. Mike was perhaps unique in that he really didn't need an advisor, and the best thing that I could do was to keep out of his way. And I think I did that very effectively. And so that doesn't always work, but in this particular case, I think it was a good strategy. So I checked on Spires because my memory's not so great, and I realized we only have one joint publication, and that came some time after Mike left Caltech, and is entitled Probing F-Theory with Multiple Brains, and there's one co-author in addition on that with us. Mike returned briefly to Caltech in 2004 as a distinguished scholar. We have a program at Caltech funded by the Moore Foundation and that enables us to bring distinguished visitors, and Michael visited under that program. So that was very good. And he also came back for my 75th birthday, which was 6 years ago. Hard to believe. And that was nice of him. So I'm glad that I have a chance to reciprocate. And I must say, when a former student turns 60, that's an indication that you're not so young yourself. So I looked up Mike's thesis. Here is the title and the abstract for his thesis. And I also give you the web address where you can find the PDF if you're interested. This is a problem that was, in retrospect, an obvious problem at the time. But Mike was the first to identify that it was an obvious problem and to select, as I say, I stayed out of the way. So he wrote a thesis on this very nice subject and addressed what was an important problem that existed at that time. According to the Simons Center website, Mike is best known for his part in the development of matrix models and for his work on non-commutative geometry and string theory, on Dirichlet branes and their relation to derived categories, and on the statistical approach to string phenomenology. And while this is true, there's much more to Mike than that, as I think we're learning during this celebration. But I'll just mention that in connection with his statistical approach to string phenomenology, he noted that when you consider the compactification of string theory from 10 or 11 dimensions down to 4 dimensions, there are a lot of possibilities, and he gave some rough estimate of convincing people that the number is indeed very large. So let me now turn to my advertised subject. So in ADS CFT, which has been so foundational really, a gravitational theory in d dimensions, d-dimensional anti-de Sitter space, is holographically dual, which means it's equivalent to a conformal field theory on the d-1 dimensional boundary at spatial infinity. And many examples have been explored in detail. The most studied example, that appears in Maldacena's original paper, relates the ADS5 times S5 solution of type 2b superstring theory to the d equal 4, n equal 4 super Yang-Mills theory. Now, it would be great if we had holographic duals to string theory and M theory solutions that involved asymptotically 4D Minkowski spacetime times the compact space, presumably. And this idea has been around for a long time. There was a nice paper written in 2003 by De Boer and Solodukin on this subject. But there was a little follow-up of that work for about a decade. And then in the early part of the last decade, work of particularly of Andy Strominger, and also he had good collaboration with Stephen Hawking and others at that time. And he explained the relationship between soft theorems and asymptotic symmetries, and that was very influential in the subject really taking off. Now, long before that, going all the way back to 1962, there was influential work by relativists who were studying what seemed a somewhat different problem. They were looking at general relativity and just asking, just as a classical theory, what are the conditions for the asymptotic behavior of the metric if the space is going to be asymptotically Minkowski four-dimensional space-time? And this is a rather technical subject. They had to choose suitable boundary conditions and coordinate systems and gauge conditions and so on, and then make technical assumptions about the asymptotic fall-offs of various functions. And based on their analysis, they concluded that there are additional symmetries in general relativity that go beyond the usual Poincare symmetries of Minkowski spacetime. And these comprise the symmetry structure known as the BMS group, the initials for these people. And the new elements were called super translations and super rotations. This use of the prefix super preceded supersymmetry by about a decade. Okay. Now, as I said, much of the recent progress is due to Strominger with various collaborators. And they've taught us a great deal about this subject, but there are no explicit examples analogous to the ADS5 times S5 story. So even though we know a lot, we don't have any specific theories to look at. So so the subject is, in that sense, in a rather primitive state still. Now, Strominger wrote a book on the subject 5 years ago, and that book he immediately posted on the archive. And so the archive version is preferable to the print version because it gets updated from time to time. And since then, there have been many developments, and it's become a rather burgeoning field. And some of the important people have listed their names here. And it's just a curious fact that 5 of these 7 happen to be women. Now, the basic fact is that the S matrix, which describes scattering of on-mass shell particles in asymptotically Minkowski spacetime, can itself be viewed as the holographic dual of the bulk spacetime theory, because you have a d-dimensional theory and you're representing it by objects that are defined in d-1 dimensions. The particle being on the mass shell simply means that p squared is 0, or m squared more generally, and that's one condition. So one of the components of the momentum is effectively eliminated, leaving you with d-1 independent components. Now, finding an S matrix for scattering in flat spacetime was the subject that I grew up on when I was a graduate student in the 1960s of Jeff Chu. But the difference was that we were interested in finding the S matrix for hadron physics. We certainly were not thinking about gravity. And now the really big question is how to deal with massless particles. And that's something that was not of interest when we were doing hadron physics, because The lightest hadron is the pi meson, which has 140 MeV or so. And so that's a crucial difference. So in this talk, I will only consider massless particles, photons and gravitons specifically. I think it's likely that those are the only massless particles in nature. It's conceivable there's a massless neutrino, but I think that's unlikely to be the case. And I'll say a little bit about supersymmetry if there's time, but it's not terribly relevant in this context. But there is literature that discusses massive particles and other space-time dimensions and even other signatures, like 2, 2 is sometimes talked about. But I will refrain from saying anything about such things. So in the case of the hadrons, as I said, the particles are all massive, and the analytic structure of the S matrix was understood quite well in the 1960s. But now that we're interested in massless particles, it's a whole new ballgame, and there are entirely new types of structures that are rising from so-called soft zero momentum particles. And the analytic structure of the S matrix is not so obvious anymore. So just a short digression, that the hadron problem led through various twists and turns to the discovery of string theory, and which turned out to be better suited to describe gravity, and it's part of a unified theory in massless particles. So starting from the hadron problem, we ended up with something that led to string theory. And these string theories actually seem to be better understood than any string theory that might describe hadrons. So that's just a sort of an aside remark. So let's get down to the nitty-gritty now with equations. So I'm going to focus on 4 dimensions. The idea is we want to talk about the real world. So we want asymptotically flat 4-dimensional Minkowski space-time. Okay? Now, is that the real world? Not really, but it seems like a really good approximation. One thing you might worry about is that it ignores cosmology. So if you want to be really fundamental, you could say, what about cosmology? But if you're willing to forget about cosmology, then asymptotic Minkowski spacetime seems pretty good. So we want to talk about massless particles, and here is a parametrization that is used by people who work in this field. And so here's a 4-vector for a massless momentum vector, and z is just an arbitrary complex number. Omega is a real number, and epsilon is plus or minus 1, depending on whether the particle's coming in or going out. So it's customary to express the S matrix as Lorentz invariant functions of the momenta, subject to momentum conservation. And this omega parametrization is very convenient for deriving soft theorems. So if you write the S matrix in these coordinates, you just look at the omega going to 0 limit for various particles, and you can read off from the amplitudes how they behave as the momentum goes to 0. But there are, and the study of soft particles is an important part of the subject. So by soft particles, one really means massless particles at 0 momentum. But there are other parametrizations. So one alternative you can do is to replace this parameter omega by a spatial coordinate by doing a Fourier transform. And so this u, since omega was actually a null energy, this dual coordinate is also a null coordinate. And when you do this Fourier transform, you're left with u, z, and z bar. And the interpretation of these coordinates is that they derive, that they parametrize null infinity. So null infinity consists of a sphere times a null line. And the null line is parametrized by u. And the sphere is given by z and z bar. We write them as covering the complex plane, but the plane is really a sphere because it's related by stereographic projection to the sphere.
The direction is orthogonal to the sphere.
That's right. When you pick a point on the sphere, that tells you what direction the particle is going.
It works over for as many gravitons as you wish.
That's right. Now, these coordinates are interesting for examining something called memory effects, which has to do with shifts of fields along the u direction as a consequence of dynamics. And there are actually memory effects of this sort that may be observable in gravitational wave experiments, not with the current technology, but with next generation. And so those are of interest too. Now the other alternative, rather than that Fourier transform, is to do a Mellin transform, in which you replace omega by capital delta. And the interpretation of delta is that it's a conformal dimension in a celestial symmetry algebra. So we're going to have a conformal field theory defined on the celestial sphere, parameterized by z and z bar, and they're going to be operators labeled by their position on the sphere, but also by a conformal dimension delta. And this transform has taken momentum eigenstates and turned them into boost eigenstates, which is interesting. So we're used to working with the S matrix in terms of variables that are momentum eigenstates, but once you do this, you're dealing with something a little more exotic. And finite energy modes will correspond to conformal primary wave functions, which belong to the unitary representations of the Lorentz group, SL2C. And these are given by dimensions delta that on this line, 1 plus I times the real number, which is where the unitaries lie. And this can be made explicit by a suitable choice of contour in defining the inverse Mellin transform. Now the goal of this program is to encode the S matrix in a dual theory defined on the celestial sphere. And this theory should associate operators, labeled as shown, to photons and gravitons. So the index S is the helicity of the particle, so that would be plus or minus 1 for photons and plus or minus 2 for gravitons. And the choice of the superscript plus minus distinguishes incoming and outgoing particles. And the idea is that S matrix elements would then be encoded in correlation functions in some conformal field theory on this celestial sphere, where you take a bunch of these particles, and that would be the corresponding S matrix element. So that's the picture that people are working towards. But the problem, well, I shouldn't call it a problem. The fact is that there is no explicit conformal field theory that's been presented yet, so you can't compute these things. But that's the goal, is to define one and then be able to compute these things. So this is, even though it's been a very active subject for a decade, it's still in a relatively primitive status. Now, the two-dimensional conformal field theories, of course, are defined in the usual way by conformal primary operators and the OPEs, operator product expansions. And in this case, we're interested in a CFT defined on the celestial sphere. And so operators can be defined by a pair of dimensions, h and h bar, which will be associated with holomorphic and anti-holomorphic degrees of freedom. But they're just related to the delta and S I introduced earlier. So delta is the sum of the two h's, and the helicity S is their difference. And the basic idea is that an operator with these dimensions multiplied by these differentials shown on the slide is invariant under conformal symmetry transformations. So that's the significance of the labeling.
Is there anything playing the role of energy momentum tensor in what you are?
Well, there certainly should be, yes. But I don't think, as I said, we don't have explicit examples yet. So there's not, as far as I'm aware, there hasn't been much done along those lines. So what's convenient for studying some of the mathematics is to expand out these operators and modes in what's a pretty standard sort of thing. Standard and familiar for people who work on string worldsheet theories, for example. You do similar things there. These exponents on the z's and z bars are always integers. So but the h's and the h bars can be either integers or half odd integers. And so the labeling is always such that the exponents m plus h and n plus h bar are always integers. So if m goes over half integral values, then so does the h. That's the understanding, but I don't say that explicitly elsewhere. So as usual, the conformal transformations are generated by the energy momentum tensor. So we do talk about an energy momentum tensor in that sense, but we're just using the abstract algebra. We don't have a representation of it in terms of the operators I showed you earlier.
And the mapping to graviton, can you do the mapping to gravitons in a suggested way?
Well, let me proceed and you'll see we'll see what happens. So we have the usual holomorphic and anti-holomorphic pieces of the energy momentum tensor, and their modes are the usual Virasoro components, which form the Virasoro algebra. I've written it here with a central extension, C, but in the following I will set C equals 0, which it generally is in anything that's sensible once you take everything into account. Now 6 of the modes, the L minus 1, L0, L1, and the complex conjugates, so those 3 belong to T and the complex conjugates belong to T bar, those 6 modes form precisely the Lie algebra SL2C. And that is how the Lorentz group is realized in this dual picture. So that's very clean and non-controversial. Now in gravitational theories, the additional symmetries generated by the other Virasoro generators correspond to asymptotic symmetries identified by BMS called superrotations. So that's an extension of, so that's an example of the extra symmetries that were discovered in the 1962 works. Which is an interesting fact. Now, but we also want to extend the Lorentz groups to the Poincare group. So we want to find the 4 translation symmetries as well. And the only way that works is to introduce another operator P with dimension 3 and helicity 0, or in other words, h and h bar are each 3 halves, and all the components commute. And if you introduce such an operator, then the 4 modes given by P plus minus half, P plus minus a half, combine with those 6 L's to form the Poincare group. And the rest of the modes of P generate additional asymptotic symmetries called supertranslations. Now, the fact that the momentum vector P mu had omega as an overall factor in it is, if you look at the Mellin transform, makes it clear that the operator P, which will also have a factor omega in it, will increase delta by 1 unit, right? Because we had omega to the delta minus 1 in the Mellin transform. So when you multiply by omega, you've shifted delta by 1. And so unlike T and T bar, P does not just generate some transformation of the celestial sphere. It changes the dimension of the operator that it acts on. Now, in 2013, Strominger showed that soft theorems that describe the zero energy limit of amplitudes in gauge theory and gravity can be understood in terms of ward identities for asymptotic symmetries. And the leading soft graviton theorem he showed is a consequence of supertranslation symmetry. And the subleading soft graviton theorem, which was new at the time, is a consequence of superrotation symmetry. And last year, he and his collaborators identified an infinite tower of soft graviton theorems, of which these are just the first two. And the corresponding conserved currents form a structure called the wedge subalgebra of W sub 1 plus infinity, which I could write down the algebra for that, but it won't. It's not particularly enlightening, so I won't do it, and it's in. You can find it in the papers. But that anyway, they did that, and it's very interesting. And that algebra captures all this information about these soft gravitons in a nice algebraic package. But this is only the classical approximation. So this doesn't even yet take quantum theory into account. And it isn't exactly known what happens in the quantum limit, but Strominger conjectures that this lowercase w gets turned into a capital W, which is another algebra that was defined long ago by people who are just studying various infinite algebras. And so this is a procedure I call quantization by capitalization. So the basic idea that leads from soft graviton theorems to conserved charges and currents on the celestial sphere is as follows. When the null energy omega of a graviton in an n+1 particle amplitude approaches 0, the amplitude has an expansion.
That's where the graviton. It's the definition of a soft graviton then.
Yes. Well, if you look at an amplitude with one graviton lag and just use classical GR to see what happens when one of the energies goes to 0, and you do that carefully, you find that you get an expansion of the form shown, just in the classical approximation. And after the Mellin transform, this implies that the corresponding operator that for this graviton will have poles in its analytic dependence on delta at values given by 2, 1, because you have this delta, you have this omega to the delta minus 1, and just because of that factor, these powers imply that you have poles at these values in the delta plane. And the various conserved currents are associated to the residues of these poles. Now, just for the fun of it, you can look at supersymmetry, but it's really not important because it's not going to contribute any more massless particles. So if it were unbroken, it would be important, but we know it isn't unbroken. But in any case, you can easily extend the algebra I showed you by introducing objects Q and Q bar that commute to give this thing I call P. And if you do that, then the modes Q plus minus half 0 and Q bar 0 plus minus half will complete the super Poincare algebra. So that's very straightforward, but not terribly important for the applications that we have in mind. Now, of course, if you do that, you're led to introduce supercharges for the other components of the Qs, which is a little silly. And you can also ask how these Qs would act on the various operators associated to the various fields. And you could even do n equal 8 if you wanted to, in a pretty straightforward way. Now, there are many tricky aspects to this whole subject, and one of the tricky aspects has to do with crossing symmetry. In hadron physics, it was very easy to understand how, using analytic transformations, you could go from the S channel to the T channel and so on. But with all this pile-up of singularities at the origin, when you have massless particles, that's all much more fuzzy and unclear. And furthermore, in this formalism, it's even more obscure. And so it's been a bit of embarrassment, I'd say, for people working in this subject, that they don't really have a good understanding how crossing symmetry is supposed to work. And that's clearly something that ought to be sorted out. And there was a paper that appeared just last month by Mazira and Pastersky, which didn't completely solve the problem of crossing symmetry, but I think it took an important first step towards understanding how that works. So let me describe to you what they showed. So let's start by considering an amplitude with 4 particles, two particles in, 2 particles out. And then so we have 4 punctures, if you will, on the celestial sphere associated with these things. And we can use the SL2C symmetry to fix the positions of 3 of them. And these 3 points on the circle, the 3 points on the sphere will define a circle on the sphere. And then they showed that the 4th point, in this case, must lie on that circle. And that the epsilons, which have to do whether they're in or out particles, have to alternate as you go around that circle. So plus minus, plus minus. So now you can introduce this invariant cross ratio, as is familiar to everyone here, I'm sure. And then you can still do a transformation on Z, and that circle can be mapped to the real Z axis. Okay?
What goes into this statement? Is this 3-level scattering?
I think so. I think so.
It's in kinematics, isn't it?
I'm not 100% sure, but I'm pretty sure you're right that it's tree level. For specific labeling, they find that the 3 different channels correspond to the 3 different regions that are defined, because when you've done this, you've put 3 of the points at 0, 1, and infinity, and so there are 3 regions defined, and those 3 regions correspond to 3 different cross processes. So now this observation doesn't itself prove that you have crossing symmetry, but it certainly seems to be an important step in that direction. I don't think they claim that it solves the problem completely. They've also investigated processes with more than 4 particles. In the case of n = 5, they find that the various cross channels tile the entire celestial sphere exactly once. So in the 4-particle case, it was just a circle, but now it's the entire sphere that's covered without any overlaps, 1. So you've broken it up into the appropriate number of tiles for each of the cross processes. How many are there? Probably 10, I would guess. So for n greater than 5, they find that they tile the sphere multiple times. And the multiplicity with which they cover the sphere grows exponentially for large n. So it gets pretty complicated. So as I said, these observations don't establish crossing symmetry, but they seem to be an important first step. So I think everything will become much clearer when you have explicit theories that we can explore, which we don't really have yet. Now, various authors at different times have suggested that the BMS group might not be the whole story, that there could be an even larger symmetry. And all the authors who make such claims have repeated the BMS analysis, but usually using some different choice of coordinates, some different gauge assumptions, some different asymptotic assumptions, and then they get a different result. And various proposals have arisen that way for extensions of the BS symmetry. And the one that seems to have appeared most often, and perhaps looks to me most plausible, is that the conformal symmetry is extended to the full diffeomorphism symmetry of the sphere. That claim appeared first in a 2014 paper by Campiglia and Lada, and it's reappeared in the work of others several times since then. each one, I think, claiming that they were the first to find it. But there have been other proposals. There's a paper last month that talked about, instead of super translations and super rotations, they had hyper translations and hyper rotations. And that was supposed to be something bigger too, but I didn't explore carefully exactly what it is they were claiming. Now, there are various reasons one might be skeptical about the idea that the symmetry is extended in this way. For example, in the case of ADS, we know very well that the dual theory has conformal symmetry and not diffeomorphism symmetry. That's utterly clear. In this case, the case is not clear, but just that fact alone suggests that maybe this is a long shot. Last week, I asked Andy Strominger for his opinion about this, and I got his permission to quote what he wrote to me in response. And he said, "There are many formulations of the symmetries, but I have found that the fact that the whole tower assembles into the loop group of the wedge algebra W1 plus infinity, the same as the one in twistor theory, very non-trivial and compelling. I suspect that is the best way to organize things." So that's Andy's take on what are important symmetries. But when he says that, he's not denying the CFT part of the story in writing that this is something on top of that. But he's also clearly not endorsing the idea of diffeomorphism symmetry, because I had explicitly asked him what he thought about that. So usually I don't appeal to the master in things, but in this particular subject area, he is the master. So I'm not prepared to expand on what Andy wrote, but he's clearly skeptical about the relevance of diffeomorphism symmetry. But nonetheless, just to keep myself entertained, I decided to explore how the mathematics of diffeomorphism symmetry would work in this context. So even though it's unlikely to have any relevance, I thought that it might be interesting, because what is the natural thing to do is, since we're defining the conformal symmetry by an operator algebra, if we're going to extend it, we should still use an operator algebra. And usually when we talk about diffeomorphism symmetry, that isn't what we do. We talk about smooth functions, which is a little different. But I mean, it'll be equivalent. It's just a different way of formulating it. It's not new mathematics in the sense of it's describing something different. It's just a different way of describing old mathematics. So, but nonetheless, I thought it might be interesting and possibly relevant in this context. So I'll just describe to you what I found. I haven't written this up. So the key fact is that the conformal symmetry generator T would now have to be extended to an operator that has additional components, which I've called J. And this so T of Z extends to J of Z and Z bar, and T bar of Z bar extends to J bar of Z and Z bar. And in terms of the conformal subalgebra, these operators appear to have dimension 2, 1 and 1, 2. And so the conformal subalgebra is just given by the components where you kill the anti-holomorphic components of J and the holomorphic components of J bar by setting the corresponding indices equal to 0. Well, actually, that isn't obvious the way I wrote it, is it? Because there's the 1 left over. Anyway, that's the right thing to do. Sorry about that. OK, so aside from a possible central extension, these operators have this algebra. So this is the algebra then that would correspond to the diffeomorphism group. And the coefficients have been determined by setting various indices to 0 and implementing the correct conformal subalgebra. But this isn't quite the whole story. There is another term that needs to be added for a reason I will explain momentarily.
Sorry, John. Are we implementing now diff S2?
Yes. Or at least I'm not implementing might be the wrong word, but I'm describing diff S2. So the fact that this is the algebra of generators of diffeomorphisms or general coordinate transformations can be shown to be correct by observing that if you look at these differential operators that I've written here, they satisfy the same algebra. And those obviously generate the diffeomorphisms of the sphere. So that makes it obvious, right? But these operators don't have dimension h, don't have the dimensions I told you. If the operator had h bar, these have dimension 1 minus h and 1 minus h bar, because one of them is minus 1, 0, and the other is 0, minus 1. But this relation between h bar and 1 minus h, 1 minus h bar is well known to people. It's given by something called the shadow transform, which relates them. And that's why I used a squiggle rather than an equal sign in these formulas. So let me tell you why we need another term. If we suppose that phi is some operator of dimension h bar, but it's not j or j bar itself, which are special in this business, diffeomorphisms are then encoded in the commutation relations shown here. These formulas have the correct behavior when you restrict to the conformal subalgebra, and they are the appropriate extension thereof. But diffeomorphism invariance is not sufficient to describe, these formulas are not sufficient to describe theories containing fields with non-zero helicity. So if you have a field with non-zero helicity, you can show there's a problem. And you find the problem by looking at the Jacobi identity involving this algebra, where if you take a j bar, and a phi, and you write down the three terms that appear in the Jacobi identity, they don't add up to 0. So there's something missing. And so it's straightforward algebra. And the missing term is easy to identify. You need to introduce a new 1, 1 operator, which I call a spin operator, whose commutation relations with a field just read off the spin of the field. And then if we add that term, such a term, to the jj bar commutator, then that fixes up the Jacobi identity. Everything is consistent. And additional Jacobi identities tell you how everything else commutes with it in a straightforward way. Now, just for the fun of it, I thought I would recast these commutation relations as operator product expansions. Usually in conformal field theory, people are happier to write down operator product expansions than all these mode expansions I've been showing you. And you can certainly do that. There's no question these OPEs are more elegant, but I find them less convenient for checking Jacobi identities. I know I can do that very reliably with these mode expansions. But I'm not so confident in my ability to do it working directly with the OPEs. So in order to save space in writing these formulas, on the right-hand side, all the j's and j bars and s's and whatnot are functions of the w's. But I don't show them because then they wouldn't fit on the page very nicely. So these are the OPEs for these operators for j and j bar that are just equivalent to the mode expansion formulas I showed earlier. And you can also talk about how S works with phi. It just reads off the spin, h minus h bar. And you can do j with phi and j bar with phi. And they're pretty similar to what are familiar from conformal field theory, with just some extra non-holomorphic factors. Or holomorphic, depending on the case. So in conclusion, celestial holography is a rapidly expanding subject that I think shows considerable progress, but it's still in its infancy. There's much more known than what I've told you, But even so, we don't have an explicit example, and we really can't get our hands dirty and really dig into it until we have something like the ADS5 times S5 story that we had for the ADS-CFT example. So this subject, I think, might eventually merge with string theory. String theory, in my view, is the right way to deal with ultraviolet divergences. And this holographic duality, in my view, is the right way to deal with infrared divergences. And we need to put them together to get the whole story straight. So that would be my dream for the long-term future. But I have no idea whether we're talking decades, centuries, millennia, or what. But that depends not only on physicists, but also on politicians, I think. And so we'll see. So thank you for listening to me, and belated happy birthday to Mike. Questions?
Yeah, thanks, Don. This is really fascinating. Do people know if this conjectured dual theory, is it supposed to be unitary, and are there arguments as to whether it's local in 2 dimensions?
I think the answer to both questions is yes.
Which ordinary principle does the unitarity follow from? Is it from some reflection of positivity or some other?
The thing that I think is that is not so familiar, at least to me, is that there are important symmetries that relate operators of different dimension. So that's, I think, something we have to come to grips with. I mean, that's a reflection of the fact that we traded this null coordinate u for a dimension. So we're really, should the holographic dual of a 4-dimensional theory be 3-dimensional or 2-dimensional? Here, based on ADS, you would say 3-dimensional. And here it sort of is 3-dimensional. But in this way of doing things, you're representing one of those dimensions by the conformal dimension, which is kind of weird.
I'm okay with it. I mean, if it's unitary, then I guess one should take all your algebras and ask if they have unitary representation.
Mm-hmm. So I'm even though I've been thinking about this for a year or so, I still consider myself a beginner, and I'm using the opportunity to speak here as an inducement to try to organize my thoughts. But as I say, the big expert in this business is really Andy.
Go ahead. His hand was up before mine.
No, it's okay.
So I'm a little bit confused. I mean, I have a theory to which I could apply all of this, right? Just perturbative, I don't know, Einstein gravity, right? So all of the data that I could possibly, in other words, I can calculate any of the matrix elements that you might be interested in computing directly, at least in some.
Yeah. Some of that's been done. I didn't show it to you.
In what sense? What is it that I want more? I want some alternative, lower dimensional, weirdo theory that will compute the same things, the same results. I'm trying to find some reduced version of Einstein gravity that will produce the same set of matrix elements.
Yeah.
I'm just trying to get
we're looking for a dual description of whatever you think the bulk theory is, whether it's pure gravity. Well, let's say it's just pure gravity. Now this subject is somehow sensitive to both infrared and UV, and so when you and the focus here has been on getting the infrared right. So the fact that I think one of the reasons why one doesn't really have fully satisfactory examples of theories is because the UV hasn't been addressed in this context. And may be forced to do what I'm hoping will happen in the long term, is merging this with string theory. And that may be needed to make full sense of this.
the point that the matrix elements that I want to deal with directly in this holographic theory, if I try to calculate them using Einstein gravity, the UV problem will kill me.
Well, no, well, it won't if you're just doing tree approximation. Clearly, it won't. But and certainly the people have written down formulas for a 4-point amplitude in tree approximation. In fact, these Euler beta functions appear, which are so familiar from string theory, appear, but with the deltas and the arguments inside there. It's a curious coincidence. Shamet.
This is a really naive question, maybe, but maybe it's an elaboration of what Kurt was asking too. You just take perturbative string theory, and let's suppose we could compute the S matrix. In principle, that gives us the data of the correlation functions of this dual theory, since they're just a rewriting. Now, normally in conformal field theory, I've learned that if you define all the correlation functions, you're done. That is the theory. So why doesn't that define the theory for us?
So let me give you the party line on infrared divergences as I get it from Andy. And what he says in one of his papers is that infrared divergences are just a technical problem when you do perturbation theory. That the full theory doesn't have infrared divergences. So the way it works is at one loop you get something times infinity, at two loops you get something times infinity squared, and you add it all up and you get e to the minus infinity.
But you never ask, in the real massless theory, you don't ask S matrix questions. You ask, I have a detector that's got some angular cross section and I see some energy go through it. I have to add up all of those rates in order to get something meaningful that doesn't have an IR divergence.
There's no question that experimentalists have known how to deal with infrared divergences for the last many, many decades, and they've been doing it very successfully. And they don't have a problem. That's clear. But the theorists still do have a problem. Because just this arbitrary cutoff on the energy and so on is a very artificial thing, and one really needs something more fundamental. And so one really wants to find a reformulation where instead of looking at the perturbation expansion, you have a way of doing the calculations which doesn't have an infrared divergence. Because, as I indicated, that's really just a problem of the formalism.
But then it comes back to my question, so where the physical graviton? How do you define the link between the physical graviton, whichever the way you define it in normal language, and these objects, these operators? How are you going to make a link?
Yeah, I heard your question. So I can't really say more than I already did, which is we're going to assign an operator with helicity 2 and some dimension which can take a range of values, delta, defined on the celestial sphere, which will correspond to a particle that enters or leaves the celestial sphere at that position. So the question is to define the theory that allows you to compute these amplitudes for which I wrote down a formal expression.
It's known since some time that W1 plus infinity is related to area preserving diffeomorphism. And I think I vaguely remember that for the case when people looked at the membrane, that they connected also this to the diffeomorphism of S2, but I'm not sure about that. Now, is that true, and how does it square with your construction?
I don't know. That's an interesting point. I should look into that.
Okay. So there's another completely orthogonal thread in this. What can I do with the S matrix so that I don't have to really look at the bulk theory? This is this whole business that Nima and friends have been working on for years now about the amplitude hedron and so on. That is to say, there's another way of organizing the calculations that you might do that sort of says the S matrix is primary and some some magic happens that allows you to understand how large classes of diagrams, if you're doing the old-fashioned
Yeah.
way, actually give you very simple results. And I don't understand how this is working, but it sounds to me, well, I'm just asking, is there any,
Yeah.
however remote, connection between these two classes of question?
If I understand correctly, that still works in order by order in perturbation theory.
Yes, that's true.
And what I think really we want here is something which reorganizes the perturbation expansion in a way that eliminates infrared divergences.
Okay, let's thank John again for discussion.